Greetings everyone, my name is Rafael and I'll present to you an overview of our work entitled Evolutionary Procedural Content Generation for an Endless Platform Game. According to Julian Tegelius, procedural content generation is the algorithm creation of content with limited or indirect user input. The content could be of any type, such as textures, sounds, environments, characters of a game, stories, poems, and so on. There are many approaches for this task, such as, but not limited to, random number generators, noise generators, evolutionary algorithms, and neural networks. This technique has been used in many commercial games over the past decades. Some recent examples of those are Minecraft, No Man's Sky, Spelunky, and Alto's Adventure. In this work particularly, the content we generate is the 2D block-based environment of a platform game. The maps are expected to be playable according to the game rules, potentially infinite, and generated in real time as the player explores the game world. This is a simple result for the approach in this work. To reach the goal, a genetic algorithm was implemented and experimented with. This approach is based on the theory of species evolution and searches for the best candidate solution for a given problem based on a fitness function. Here, each candidate solution, just like a biological individual, is represented by its genetic code that dictates its characteristics. The idea is that a group of individuals should evolve over the course of generations, such that after n generations, it is expected that the best individual is a candidate solution that meets the initial requirements. Here, each individual represents a finite chunk of the infinite map. Because we wanted each individual to be more easily dynamically appended to the game world in the x direction, we implemented it as a doubly linked list. Each node of this list is a gene column that has information for placing all the blocks in the y direction for its respective x position. Therefore, when new chunks are created, they may be easily appended either to the left or the rightmost corners of the game world dynamically. To evaluate how good an individual is, a fitness function outputs a numerical score that takes into account the density of enemies and power-ups present in the chunk, such that they lie between a reasonable range of values. It also accounts the width of holes in a series of jump simulations from any given safe block, such that it should be possible for the player to reach any safe block from any other given safe block by performing a jump. For every pair of parents chosen to undergo the crossover operation, we search for a compatible crossover point in a central region of the chunks represented by the parent's genetic code. By compatible, we mean that the ground height difference of both parents at the chosen point should not be higher than the player could possibly overcome by jumping. Then, the generated offspring inherits its left chunk side from one parent and its right side from the other. When a new chunk has to be generated, an initial population is initialized with information of its static neighbor chunk and a new complete randomly generated chunk. This ensures that the fitness function returns a score that indicates how well this new generated chunk fits together with the neighboring area it will potentially be appended to. Then, for each new generation, the best individuals from the previous generation are selected based on analytism rate. Then, pairs of parents are chosen with probability proportional to their fitness values, and crossover operations that were mentioned before generate the offspring. Then, the elite and the offspring are unified to form a new population. Eventually, this new population may undergo mutation operations with a low probability, which is the mutation rate. This iteration happens for a number of generations, such that after max generations, the best individuals satisfy the requirements encoded in the fitness function. We performed a number of tests, changing some of the parameters, such as population size, mutation rate, and elitism rate. The graphs you see here show the evolution of the fitness of the individuals for the first 1,000 generations. Here, these 4 graphs correspond to simulations of populations of size 10. Notice that a lower mutation rate of 0.5% is more stable and tends to converge to higher fitness values, whereas mutation rates of 2.5% or more are very unstable, especially for low population sizes. When we increase the population size to 50, like here, and 75 here, the conversion to higher values is smoother and the processing times are still acceptable. However, when we increase the population size too much, say for 250, the processing time also increases significantly. So one should increase it with caution and experiment what works best for the game rules and the hardware requirements. Some points that could be further improved is changing the stop criterion from a fixed number of generations to dynamically stopping the evolution when the fitness increase rate is not significant anymore. Furthermore, this approach could be expanded to 3D if the doubly linked list is replaced with a slightly more complex data structure. Thank you very much for your attention, and if there are any further questions, we look forward to answering them in the Q&A session.